using 4 trapezoids. So x squared plus 2, let me make this a little bigger here. And since we're only going to go from 1 to 3, we don't necessarily need this part over here, but this would be a parabola. It opens upwards, vertex of 0, 2. But since we're only going to go from 1 to 3, we really only need the stuff that's happening on this side of it. So what we're going to do, we're going to approximate the area underneath this curve, but instead of doing rectangles, we're going to do trapezoids. So the way we're going to do this, you're still going to have to figure out what is our change in x. So how can I go from 1 to 3 and end up using 4 trapezoids? So it's the same process. We're going to find the difference in our interval, so 3 minus a 1. So we're covering a unit, 2 units. We're going to do that in 4 steps. So that means each step should be 1/2 of a unit. So if we cut this in half like we did with the ones we started with the rectangles, that should give us the makings of 4 of these. And we now know this would be 3/2, 2, 5/2, and then 3. All right, so now the way we're going to get trapezoids, if I go up from 1 and then 3/2, if I just go up from each of those, hit the curve, put a dot like we did when we did rectangles, and then just right away connect those, don't we end up getting a trapezoid right away? So that would end up giving us trapezoid number 1. I suppose a lot of times I kind of we review a little bit what a trapezoid looks like. So a trapezoid, the big thing is it has one and only one set of parallel sides. So this is a trapezoid. These are our parallel sides. The height is the line that connects directly in a 90-degree angle your 2 bases. So this is our height. And then the parallel sides are considered your bases. So when we use this formula, so you have to review this little formula here, that's the area of a trapezoid. The bases are always your parallel sides. So B1 and B2 are the parallel sides. And then the line segment that would connect those would be your height. That's how we would be able to plug into all of these. So that's probably something we should have talked about real quick at the beginning. Just make sure you remember what a trapezoid is, the area, what all those components are that make up the trapezoid. All right, so we have trapezoid number 1, and then all we're going to do to get these other trapezoids is go up from 2, hit the curve, connect those together. We now have trapezoid number 2. Go up from 5/2, and then just connect all of those. And what we should then see is we end up with the 4 trapezoids like we're supposed to. Okay, so from there, if I'm going to estimate the area, I'm going to say that my area, and this is an approximation, we're now just going to plug into this formula. So I'm going to have a 1/2 because that's the area of our trapezoid. I would then need the height. So the height, think about what how all these trapezoids look. So let me erase this initial one. What we're dealing with is a trapezoid this is called an isosceles trapezoid for those who are really good with their old geometry terms, because we have a 90-degree angle right here. We're dealing with this trapezoid in number 1, but just understand this has been rotated 90 degrees. So all your rotations that you spend a ton of time on in math 1 and 2, rotate this thing 90 degrees counterclockwise, and you get a trapezoid that looks like this. That's what we have down here in trapezoid number 1. So what you want to understand, the first thing that is different, it's both the same and different at the same time, is when we do our change in x for this, so this element right here, the change in x is not the base like it was for the rectangle. The change in x is actually the height. It's this segment right here if that got rotated 90 degrees. All right, can we see that? So our height is actually the change in x. So when we go to multiply by our height has to be this 1/2. Then what we would need to do is figure out what are the bases of that first trapezoid. So if I go to number 1, the first place where we touch it, notice how we're hitting the curve at that point. So whatever the y coordinate is at this particular point, this would be the length of that first base. All right, so for this spot right here, we need to figure out what is that length right there. So you're going to get the y coordinate when x is a 1. So here's our equation. Plug in the x coordinate of a 1. And when you square 1, add a 2 to it. That first base should be 3. All right. The next one is going to hit the curve right here. This would be base number 2. Is this for trapezoid number 1? Come on. There we go. So this is base number 2 now. So what we now need to figure out is what is the length of this one. So it's the y coordinate at 3 halves. Right? So what we now need to do is take your 3 halves. And this. Plug it into our equation. All right, and when we do that, you're going to get that to be 17/4. So this here, if we throw this into our calculator, that's going to give us the area of trapezoid number 1. So here's our first trapezoid. And then we just continue on. You're going to do 1/2 because that's the half in the formula. We still have to multiply by the height. The height for all of these is also a 1/2. And then now this is going to be trapezoid number 2. So if I need trapezoid number 2's first base, don't we already know that one? Because if I go to trapezoid number 2 right here, its first base is this base here that we've already calculated for the first trapezoid. And that is going to give us that same exact length of 17/4. When we go to the next one, so for trapezoid number 2 here, we now need to figure out what is the y coordinate up here. So you're going to take your 2, plug it into x squared plus 2, square it, add an additional 2, and we should get that to be a 6. This will give us the area of trapezoid number 2. Plus trapezoid number 3, 1/2, that's part of the formula. Our height for all of these is also a 1/2. This base that we just found for trapezoid number 2 would actually be the first base for trapezoid number 3. So the 6 starts this one off. And then that last one of 5/2, you take that, plug it in. So we take our 5/2, evaluate this. That should give you 33/4. This is the area of trapezoid number 3. All right, and then last but not least, the 1/2 that's part of the formula, 1/2 that's our height. The base of trapezoid number 4, the first one, would be the base that we just found here for trapezoid number 3. That is our 33/4. And then finally, the last base for trapezoid number 4 would be at 3. When we hit the curve up here, plug that in, we should get an 11. Doing it this way, we're just breaking it up into our 4 trapezoids. We would then add all those together. And if you had the paper, you can see this is all done for you here. But we kind of like writing it out since most of you don't have this. So when we now do all of this, this would be the approximate area underneath this curve. All right. Similar questions you're going to get asked in terms of, is this an over approximation or an under approximation? If we look at this particular graph, notice how our trapezoids go just outside the curve. So we would be accumulating just a little bit extra area. So the real area would be just a little bit smaller than what we just found it to be with this 51/4. All right. So that's the approximation using trapezoids. There is something that is called the trapezoid rule, which will make this a little bit easier, and that's this down here. All right. And what this is now based off, and the reason I like doing this first one the long way, let's separate these. So here are our 4 trapezoids right now. So trapezoid 1, 2, 3, and then 4. If I were to ask you to identify what's common in all of those, notice how this half is common in all of them. And the reason this half is common in all of them is because that's the area of a trapezoid, 1/2 times your height, and then the difference by sum of our bases. All right. The other thing that is common in all of these is this second 1/2. And the reason this is common is because that is the height of all of these. So the way that we got this half was the whole b minus a over n. So whatever the height is would be the same for all of them. So we really could factor those two out. We could pull out the half and we could pull out our height. And then now notice the little pattern here. Whatever our first base was, this 3, that's only going to go in the one time. The initial base is only used once. So that's this guy up here. Notice how he is not shared between different trapezoids. But if we go to this second one, notice how we have a 17 force here and a 17 force here. So we would just double whatever that second base was going to be. And that is because this second base is shared between trapezoid 1 and then trapezoid number 2. Well, this base gets shared, this base gets shared, and we continue to share the base until we get to the last trapezoid. And notice how the last trapezoid, that base would only get used one time because there's nothing to the right of it. So what the little formula then tells us is we continue to double all the bases in the middle until we get to the last trapezoid, whatever that nth trapezoid is. And then notice how our coefficient is once again just a 1 because it wouldn't have gotten shared. So this will make it a little bit shorter. It makes it a little bit quicker. But we can do this as long as we have this common change in height. All right, that kind of makes some sense, hopefully. Okay, so for number 1, we're going to start with a nice, easy, quick one in terms of how we are going to do this. So draw in what this graph looks like. And again, you don't necessarily need the left-hand side because we're only going to go from 1 to 2. And it doesn't have to be to scale. Give yourself some room to draw this stuff in. So 1 to 2. And I want you to do 4 trapezoids. We're going to split this up 4 ways. So the first thing we have to do is figure out our change in x. But this now in a trapezoid rule is actually the height of our trapezoid. Where in the rectangles, it would have been our bases. That's the first thing that's a little different. So we're still going to do the difference in the interval of 2 minus a 1. And then divide that by the number of trapezoids. So now the height of all of our trapezoids should be 1/4. Now, I'm going to draw these in initially, but drawing these in isn't quite as important. Let's label them first, and we'll talk about that. So this would be 5 fourths, 3 halves, 7 fourths, and then 2. Red is really tiny. The nice thing about this with rectangles, depending on if it was inscribed, circumscribed, midpoint, you had to kind of think which points do I use. There's no thinking here. Every single one of these, you go up, touch the curve, connect them, you're going to use this. So one of the things that a lot of times you'll get tested on is the idea that even though there's only 4 trapezoids, right, we're supposed to, if we look at how many times we hit the curve, we actually are hitting the curve 5 times. So there's actually 5 bases. So there's always 1 extra base for the number of trapezoids. So that's something you want to kind of file away. That's something that at some point you'll probably get tested on. So the way we then list these or do these is I'm going to list, and we don't have to worry about C's and all that stuff with these. We're going to list the 5 places where we hit our curve. And we're going to hit them everywhere. So there's not a lot of thought here. Let me get this here. Give me a little room to operate. All right, and then what we need are the lengths of our bases. So this is a pretty quick and short one. Because our function is just x squared. So we can just square all of these. If x is a 1, my base is 1 squared, which is 1. If x is 5 fourths, plug it in here. 5 fourths squared is 25 sixteenths. 3 halves squared would be 9 fourths. And then 49 sixteenths. And then 2 squared is 4. These are our bases. That's the length of all of the bases. All right, so now we're going to plug into our formula. We know we have the 1/2 because every single trapezoid, when we find the area, that's part of the formula. So you're going to put that first. And then we multiply that by our height. Our height in this case was the 1/4 that we got right at the beginning. So every trapezoid has a height of 1/4. And it's the whole idea that if we look at base number 1 is only used by one trapezoid right here. So we only put that value in one time. But if I look at base number 2 right here, this base would have been shared by trapezoid 1 and trapezoid 2. So you're going to double the 25/16. The 9/4 is the third base. That would have been shared also. So you're going to double that one. The 49/16 would have been shared. So 2 times 49/16. But eventually, we get to this last base right here. And that would only get used the one time. So we only put that one in once. So if you notice, the first base and the last base go in once. All the others would have gotten shared, so we double it. All right. So throw that into your calculator. I just did it before we got here. And that should give you 2.34375. Then, based upon its concavity, whether it's increasing and decreasing, notice how the trapezoids are a little bit bigger than the real area. So that's an over approximation. We have a little bit more than what we would actually have there. So let's see how close. And this will be a little review from last semester. We know how to find the exact area now, correct? Here's our approximation. We can do the antiderivative of this, x cubed over 3 from 1 to 2. We would get 8/3 minus 1/3, upper limit minus your lower limit, which is 7/3. So that's 2.3 repeating. So this is the exact area. Notice the trapezoid rule gives us a really, really close value to what the real area would have been. Okay. All right. So then at this point, you're probably wondering, well, why do we got to do the trapezoid rule if we now know how to find the real area? That's a very valid question, and I'll answer that in about 5 minutes. But I want you to see one more here where we got to go through all this work. And then the back page, or the next page, you probably don't have a back page to even see what I'm talking about, unless you printed it. You'll see why this is necessary. So for this last one that we got to go through all the work here. Draw in 4 minus x squared. So our vertex is here at 4. And then we'll go -1 to 1. What we need to know is what is the change in x. So if I find my change in x, you're going to do 1 minus the -1 over 4. So that's a half. And then again, different than our rectangles, that's actually the height of all of our trapezoids. So that tells us we're going to move over to a -1/2, another half to 0, another half to 1. It's ugly. And then that should set up our 4 trapezoids. All right, so we go up from a -1, hit the curve, -1/2, hit the curve. Notice how now these trapezoids will be underneath the curve. So this should end up being an under approximation, whatever we get. But again, the nice thing about this is you don't have to think which x coordinates am I using. You're going to use all of them. So even though we have 4 trapezoids, you're going to end up with 5 bases. So we're going to get one at the -1 value, -1/2, 0, +1/2, and 1. All right, so now figure out these lengths. So now we're just going to evaluate when x is a -1, what's the y coordinate, because that's our height. So take your -1, square it, subtract it from 4, should give you 3. Take the x value of a -1/2, square it, that's a 1/4. So what, 4 minus 1/4 is 15/4. Next one's easy, that's just going to give you a 4 right away. And then whatever I got at 1/2 and -1/2, those should be the same. So the 4th base should be a 15/4 also. And then the fifth base, if I take a 1, plug it in, should give me the same thing that I got earlier with a 3, which is a 3. So these are our bases. Once we know that, we can come over here, set up our rule. We have the 1/2 from the formula. And then the height would have been the 1/2 that we found at the beginning. And then now we multiply by all of our bases. The first base here would have been used once. So the 3 goes in the 1 time. But the second base, the third base, and the fourth base, these all would have been shared by a trapezoid to the left and to the right. So you're going to double all the ones in the middle. So double the 15/4, double the 4, and then again double the 15/4. But you get to that last one, this last base, the fifth one would have only been used once, so the 3 only goes in the 1 time. All right, so fill that in your calculator. Where do I have this? That should give you 7.25. This would be an under approximation. We're losing these. So let's use our approximation symbol here. Not that you need to write this down, but the real area would have been 7 1/3, and you can see then how close that is. It's just a little bit less than the real area. All right. But again, we could find the real area right now, so I don't necessarily need you to do this. Don't do this, in fact. But if we just evaluated this definite integral, that will give us the real area. All right, which again kind of bodes the question, why are we doing the approximations now if we have a method that will give us this real area? Okay, and the answer to that question is the only way we're going to be able to get the real area is if we know our function, if we can define whatever model we're dealing with an exact function. If we don't, and all you have is a table of data, then there is no way for us to do an antiderivative and plug in the upper and the lower limit. So this back page or the second page, however you have this right now, or eventually when you get your hands on this, when you get to pack it, this is really where the trapezoid rule is going to get used the most. Same with our rectangles, when we just have a bunch of data. So this says the chart below gives values of some function f of x at certain values of x. It says using a trapezoidal approximation of 3 trapezoids. And then this is important. So every option in Word available to me in terms of this is italicized, it's bolded, it's underlined. This little phrase here will not always be exaggerated like I currently have it. You have to read and find this every time. If you look at number 4, we want our trapezoids to have equal height again. That's just like the ones we did on the front page. Every single one of them had an equal height. If I go down to number 5, I don't say that our heights are going to be equal. This says your heights are going to be indicated by the data in the table. So when you read through these problems, that phrase is really, really important. So make sure when we go through those, because I won't always have it highlighted like that, that we're looking for this. But right now, we're still going to do these with equal height. So when we go through this, first thing we have to do is figure out if I'm going to approximate from 0 to 12 the integration of this unknown function. The first thing we have to figure out is our height. So the height is always our change in x. We are going from 12 to 0 because those are the limits of our integral. I want you to do this with 3 trapezoids. Oops. So we are going over every step by 4. So if I start at 0, which I have to because that's the lower limit, and I move over 4, I like making mine look like trapezoids, so it's up to you if you want to do that. But I'm going to actually draw this in to make it look like a trapezoid, but I'm going to go from 0 to 4. If I go another 4, that's going to take me to 8. So I'm going to make it look like a trapezoid again. And then the last one, I go over to 12. So here is trapezoid number 1, trapezoid number 2, trapezoid number 3. Just like we did with the graph on the front page, we would have hit our curve here, 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 and here. So while we have, again, 3 trapezoids, there's going to be 4 bases. Now, the tables are our friends. The tables you're going to like. These are the easiest type. It's much easier and much less work because we're ready to throw all this in right now. So with the trapezoid rule, we know we're going to have our half. We then know we have to multiply by our height. We have that right here. Our height is 4. So we plug that in. And then the next thing we plug in are all of our bases. But we don't have to find these anymore. These are given to you in your table. So if I would have hit this right here, isn't our functional value the height when we did those couple of problems on the front page? So our first base would have been the 3. The next place I hit it was over here at 4. So the next height or next base would have been the 10, and we would have used that one twice. It would have been doubled. 15 would have been the next base that would have been shared. So we do 2 of those. And then our final base would be the 20. That would have only been used in trapezoid number 3. So we only put that one in one time. And then very quickly, everything you need is there. I did not have time to plug this in, so I don't know what this one is. This should be a little easier though, right? 3, 20, 30, 20, 70. Is that 146? Hopefully. All right, so that's our approximate value of that function, which we don't know. Okay. This way, unless I give you more information, we don't know if that's an under approximation, over approximation yet, unless I were to tell you the concavity and increasing and all of that. All right. All right, so number 4. Similar idea. We're going to use some fancier words. I now tell you that this is a velocity table. So we're going to do this. It's in meters per second. So this is our velocity row. This is our time of a buck flying in a straight line. I want you to use a trapezoid rule of 3 trapezoids. We want our heights to be equal, and we're going to go from 0 to 18. So that just so happens to be the full table. So we're going to go the entire table, and we're going to do 3 trapezoids. So again, we need to know what's each step size. So our height is our change in x. In this case, that means 18 minus a 0 divided by 3. We're going to go step size of 6 every single time. So starting at 0, I would have gone up. I would have touched the curve if we had a curve, and we would have moved over to, I went too far, 6. And we would have gotten our first trapezoid. If I go another 6, that takes me to 12. This would be my second trapezoid. And then the final one to 18, that would be trapezoid number 3. So if I now want to approximate this, so we don't have a velocity function, we don't have an exact model, but we have some data points along the way, we can now use this to approximate its integration. So 1/2. Our height in this one is the 6. And then if we go to all of our bases, this would have been base number 1, this would have been base number 2, base number 3, base number 4. So the first and the last one only go in once, so the 5 goes in once, but then you would double the 20, oops, and then double your 30. I need my eraser to work. But the 40 would be the one that, again, just used one time. All right, so when we get this now, I also want you to explain the meaning of what we just found when we get this answer. All right, so if you're ahead of me, what do we get here? 40, 145, 3 times 145, 60, 145. What do we get for this? I don't remember it being this big. 12. 435? I'll get that? Okay, good. All right, so usually when you explain it, I want to have correct units. So a couple of different ways to now approach this. One is just stuff that we've talked about. If I integrate my velocity, right? So if we're integrating velocity, doesn't this have to take us to a position? Yes. So this has to have a unit. Since our position in this problem was in meters, this would have to have a unit of meters. Meaning what we just found, this is the change in the, what do we have going on? The distance. The fly traveled. And then just like with our rectangles, when we explain those, you have to explain your limits from t equals 0 to t equal 18, and then these have to have the appropriate units also, which is seconds. So then how does this give us meters, like just in terms of units. Just make sure we understand this now. The 6 here, that was 0 to 6, 6 to 12, 12 to 18. That's your time unit, so it's every 6 seconds. So that was what 6 was. And then think about what the unit of 5, 20, 30, and 40 were. So 5, 20, 30, 40. They all had this unit of meters per second. So when we multiply those things together and those cancel, that's why we ultimately end up with this being a unit of meter. So the whole idea of area as an accumulation of change, as an antiderivative, we want to make sure that we don't lose sight of that. Okay. All right, and the last one I want to make sure we get to. So 6 we probably won't get to, but you'll survive. I'll make sure you see one like that in due time. All right, number 5. So the first one now where this says your heights are indicated by the data in the table. So I tell you this is an acceleration table, so that's why this is now meters per second squared. You're going to use the trapezoidal rule, and I want you to approximate the integration of this acceleration function that we don't know the exact function for from 2 to 8. Notice how I don't tell you how many trapezoids to use. That is not unusual. So if you're not told how many trapezoids to use, it is implied that you do a trapezoid in every single interval. So we go from 2 to 3, and then to the 6, and then to the 8. So this should give us 3. So if you're ever not told how many trapezoids to use, you're going to do one in every single interval. All right? It's implied. So now, understand how this is a little bit different. Let's say I ask you to go do this. So we're going to say if I integrate my acceleration multiplied by my change in time, I would say that I'm going to have the half for sure, because that's part of the trapezoid. But if I now ask you for your heights, the way we've been finding the height is your change in x, in this case, I suppose change in time. We would have done 8 minus 2, and we ended up using 3 trapezoids. So that would be 2. So our issue right now with this is my change in time should be 2. But if I go from 2 and I move 2 units, is there any information at 4? Because I should be going from 2 to 4. No, there's no information given. What we now have is let me erase this so you can see this. And I'll do it in red because this is what I would kind of recommend doing. Our change in time for trapezoid number 1 is 1. Our change in time for trapezoid number 2 goes from 3 to 6. Notice how that's a 3. And then our change in time for trapezoid number 3 is 2. Notice how those are all different. So we can't just fill in this one spot with a common height. So what this simply means, it's a little bit more work, but still nothing crazy. This just goes back to us having to do these as individual trapezoids. So if I'm going to do trapezoid number 1 only, its height would have been 1. And trapezoid number 1's bases would have been 10 and 14. When we go to that second trapezoid, we're going to have a 1/2. But its height would have been the 3 here. That's our change in time. And its bases would have been that 14 again, along with the 15. So we do 14 plus 15. And then our final one, the third trapezoid, has the 1/2 that we have to have. Its height, though, is 2, because that's its change in time. And then its bases would be 15 and 20. So when it has these indicated by the data in the table, what that means is these are probably not going to have a common height. So you just have to set them up individually. But again, all the data is given to you in the table, so we just copy it right from there. Okay. If we ask you to explain this, I don't know what this is offhand, but this should be the change in velocity, because we just integrated our acceleration. And then from t equals 2 to t equals 8 seconds. All right. All right. So with that, I mentioned it in passing at the beginning, so sorry to do this. I do feel somewhat conflicted about giving you homework the first day back. Nonetheless, I'm doing it. Here's the assignments. All right, so you can find this on the modules, just underneath the notes if you had that trapezoid rule assignment, or if you go to the assignment tab, it's Probably really slow right now, but it's embedded in there. You can click on it, you'll see it. If you want to print it, you can. If you want to just look off of the screen, you can, but it'll be in here too. All right, it'll be due Monday afternoon, so I'll give you some, if you had any questions on Monday real quick, we can talk about it. I can remind you in case you forget after the long break that you have an assignment that I'm that guy that just gave you homework. I'll remind you on Monday and then get that uploaded before the night, okay? All right, good seeing you guys. Hope you had a good break. Class is over if there was a bell, so we'll see you guys later. Have a good night. All right, see you on Monday. Yes, ma'am.
The assignment's the one underneath the 5.5, right?
Yes. Yeah. Yeah, it should be. It should be a bunch of tables. I'm freezing.